we're continuing with probability distributions, right? So we've already done these first two learning objectives, right? Probability distribution, right? I'll remind you what that is just because you haven't, but you've done that. You use the probability to calculate probabilities. When I'll talk about expected value, right? So just like a set of data has a standard deviation and a variance, so does a probability distribution. It also has a mean, which is actually the same thing as the expected value, right? So we will go through a couple examples of this, right? Where are my notes? Notes. In here earlier, I've looked at them so many times. Oh, they're already out. Okay, perfect. So just a reminder, this is what a random variable is, right? Right, and this is what this whole section is on, right? Discrete probability distributions. That's the title of this chapter, right? So we're talking about this. So a probability distribution assigns a real number to each outcome of an experiment, and in a discrete one, there's some finite number of possibilities, right? You roll a dice, there's 6 numbers. Each one has a probability of 1/6 coming up, right? We had other examples where I flip 2 coins, right? They come up, right? I can create a distribution by numbers of heads. 0 heads comes up 1/4 of the time. 1 head comes up 1/2 of the time. 2 heads comes up 1/4 of the time, where each number, right, has a probability that's associated with it that's different. Right now, those probabilities must always what? And in probability distribution, the probabilities can't just be anything. Well, each has to be less than 1, correct, and greater than 0, right? Greater than or equal to 0. And what is the total of the probabilities in a probability distribution? 1 or 100%, right? Because that's everything, right? If they add up to less than 1, right? If they add up to more than 1, that's obviously ridiculous. If they add up to less than 1, that means there must be some other possibility that's not being included in the distribution, in which case it's not a full probability distribution. So they always need to add up to 1. Here is an example of one. You can always represent them in a histogram, right? And you can find the probability of like a set by adding these up. So if I wanted to find the probability that x is greater than, or sorry, less than or equal to 2, I could add up probability x is equal to 2 to probability x equal to 1, probability x is equal to 0, okay? Now, so everyone remembers learning this. This shouldn't be any, this isn't anything new under the sun, right? Does this sound familiar? Okay, so let's now think of a game of chance. Right? So you have your cousin Drippy. I don't know how he got his name, but that's his name, Drippy, right? And he has, I don't know why, he's offering you to play this game, right? So you give Drippy $1, right? And for this $1, he will give you a dice to roll, a die to roll, right? Oh, there we go. This is something we were talking about, right? If you roll a 3, he will then give you $10, right? So what do we think? Is this a game that you would want to play? We're not sure. Right, well, you pay $1 and then if you get it right? So let's kind of try to do an analysis of whether this is a game you would want to pay or not, right? So let's look at let's let x, right? So let's let X be the amount you win / lose, right? So more precisely, let's talk about, let's say that X is, right? It's on top of it, but let's say X is equal to, what do I want to call this? Change in your net worth, right? So if X is equal to the change in your net worth, right? It could be negative or it could be positive from playing this game, right? So let's look at the different possibilities and see what happens with each of them, right? So there are two different outcomes, right? There is winning and there is losing, right? So winning and losing will each have a different dollar amount associated with them. This is how you play these games. So if you lose, what happens to your money? You lose $1. So what would that be as like a value? -1, right? What would be the probability associated with -1? So what's the probability associated with losing $1? Probability of losing $1 is pretty clear, everybody. The dice lands on a 3, he gives you $10. So if it doesn't land on a 3, he doesn't give you anything. So the probability of losing that dollar is, everybody? No? 5 out of 6. 1 out of 6 is the other probability, right? We all clear that why this is 5 out of 6, right? So if you have the function, right, you can think of the probability distribution as a function, right? I plug in 1 to p of x, I get out 5, 6. The probability of having a net change in value of -1 is 5 out of 6, right? Here's another question. So that's losing. The other outcome is winning. What is X associated with winning? Who thinks it's plus $10? It's 9. Why is it 9? Yeah, you lost that dollar. Well, anyway, right? That's a mistake that students make with these things, right? So make sure to account what you have to pay. So, and the probability associated with this 9 is 1/6, right? This is a complete probability distribution. There's just not a lot going on, right? Because it's a simple game, right? 5/6 of the time you lose $1. 1/6 of the time you gain $9. So how could we figure out whether this is a good game to play or not? Any thoughts? None. Any intuition? Is this a game that's favorable for you to play or unfavorable? What do we think? Yeah.
I might get 9.
Mm-hmm.
I throw like 6 times.
Right. When you okay, so you hope or you actually kind of expect it, right? Because you expect, right? Obviously, it's not exactly, but we already talked about the law of large numbers, right? If you play this game many, many times, you should win 1/6 of the time, right? And then you should lose 5/6 of the time, right? So this is what you're actually you're doing. right? So let's show the calculation that we're doing this, right? Five-sixths of the time, right? Let's say I am going to lose $1, right? Let's think of it this way. Expected value is difficult for students to think of in a probability distribution, but it's easiest in this, right? So notice what I did is I took each value of x and multiplied it by the probability of that value coming up, right? When I did that, I got 2/3. This is a positive number, right? So this means that you are correct. You should want to play this game. So what does this mean, right? If I played it many, many times, right, it won't be exactly, but if I played it many times, law of large numbers says over time, right, the amount that I lose should be roughly 5/6 of those times, right? Everyone agreeing with me on that? And 1/6 of the time I should win. So 5/6 of the time I am losing $1. 1/6 of the time I'm winning $9, right? If I multiply these and add these, I end up getting 2/3, right? Which is roughly 2/3, right? Which as a dollar, right? Notice this is a probability. This is a ratio, so it has no unit. These are measured in dollars, right? So I multiply a unitless thing by $1 plus a unitless thing by $1, I get dollars. So what this is saying is over time, right? If I played this game many, many times, sometimes I would lose, sometimes I would win, but on average, each time I play, I would average out every play, increasing my net worth by 67 cents. So that's a good game to play then, right? Because this number's negative. If this number's positive. If it were negative, this would be a game that you would not want to play. If this were 0, you could say, then it's just your risk appetite. Do I enjoy gambling or do I just want to sit home and watch TV, right? So that's what this is. Now, obviously, if I play this game repeatedly, I will never actually gain 67 cents on any particular play, right? Each play you're either gaining $9 or you are losing $1. But if you average them out, right? I know we're not supposed to say average, right? Right? If I play many times, right, and I add all those values together, divide by the number of times to play, this should be my value that I get if it's big enough. This is my expected mean for each play. Does everyone kind of understand what I'm saying here? Okay, so what this is called is your expected value. And we use the notation E of X, right? And I'll talk about that notation in a second. But any questions on what this number represents? Okay. So if we get this, can we, while I take attendance, can you talk to the people around you? What is this 67 cents, right? Talk about what is that, right, in the context of this. Talk about why the word expected value makes sense. Talk about how you conceptualize what this 67 cents is. Does everyone understand what I'm asking you to discuss with the person around you? All right, let's do that. All right, so I heard some of you guys talk about it, but it'd be better if we maybe I'll talk about it. So who wants to explain how they conceptualize this? Anybody willing to? Oh, okay. I'm going to start cold calling. Well, not cold, but I'll have a way of doing it later. So expected value, right? Is it an average? Well, it's kind of what you would average out, right? We don't like to use the word average. So it's like an average kind of, but what it is kind of is it's a mean. It's mean like, right? It is if you played many, many times, it is the mean amount of money you would earn on a play. Even though in this particular amount, would you ever earn exactly 67 cents on a play? Class, would you? No, never, right? But it's still the mean, right? The mean value oftentimes is a value that's not included in your set, right? But it's definitely not the median, it's not the mode, right? So this is an average value. It is what you expect to happen, kind of. It's called expected value, even though you don't expect to get that exact value. It is what you expect to happen over time, right? If you play many, many times, that is your expected net worth per play, right? So roughly, right, if you were allowed to play this game 100 times, you would expect to get roughly $67, right? That's you could get more, you could get less, but they would fall around that in a way that averages out. So it is the mean if the experiment was repeated many times. So the formula for expected value is this. The expected value, right? So let's say you have so this is discrete, right? So in a discrete thing, there are a set number of possibilities, right? So in this case, there were how many possibilities? It was actually quite simple. There were how many possibilities? In my table, there were how many values of x? 2 possibilities, win or lose, right? Those of you who said 6, you may have been thinking, well, there's 6 dice rolls, right? But all the non-winning ones, right, are equivalent, right? So in this case, we just did this part, right? So it is the x associated with the probability, associated probability, right? Another way you might see this formula, right? So the associated probability, right? You might see this as, sorry, I don't know why it flipped here. Sometimes you might see this as everyone seen? I don't want to get too formal with the sigma notation because that's not a big thing here, but that just means it is the sum of all the x's multiplied by the p of x's, right? Remember, I taught you there's a different type of mean. What type of mean did you multiply like individual values by? This is a weighted, right? This is an example, right? And now I'm just kind of, the reason why I didn't have it here is now I'm thinking about it. This is an example of a weighted mean. Kind of. It is a weighted mean, right? The probability is the weights, right? Because, right, as Alessandro was saying, right? You were telling me you would expect to win like 5 out of 6, 1 out of 6, right? So you were kind of multiplying the losing, right, by 5 out of 6 and the winning by 1 out of 6, right? Instead of just averaging, taking the mean between -1 and 9, you're taking a weighted mean based on how likely certain outcomes are, right? So this is a weighted mean, right? And when you do the weighted mean, you have to divide by the total weight. Since the probabilities always add up to 1, you don't have to divide, right? So this is a weighted situation, right? And notice what you're doing is exactly that, right? So we had, so in this case, notice this was our table. I'll just draw it here. Notice we did exactly this, right? So there's only this part of it. So it's the x value, -1 times 1/6 plus 10 times 5/6, right? So one thing I want you to notice is that e of x is a value, right? So important thing to understand is e of x is not a probability, right? It is an expected amount, right? It is measured in whatever units x is measured in, right? So it is an amount of dollars. When you're trying to find out a probability, you should be adding probabilities, right? A common mistake students make is when you have a large probability distribution, right? And I say, what's the probability of x is less than 7? They multiply the x values, right? So I'll show you what I mean by that, because some of you might make this mistake, right? So when you are doing an expected value calculation, you should always complete it. There is never a time where you will ever truncate this calculation. You understand what I mean by like adding some of these values together and not all of them. So the expected value, right, is the mean of your probability distribution. It is the value that you would average out if you were doing it over and over again, right? Questions on what an expected value is? Okay, so remember, this is the TV viewing, right? At the beginning, we talked about this on Wednesday, right? So I want you to do two things. So one, I want you to find the expected number of hours of TV viewed, right? Find the expected value. And I want you to calculate P of x is greater than or equal to 2. All right, can you do both of these on your own, and then we'll come together in a couple minutes. You have the formula from before. You can talk to people around you. You don't need to do this completely on your own. Anybody get 2.4? All right, you got it correct. So let's do that. So the probability distribution, right? It's also a weighted average. So notice it's going to be 0 times the probability of 0, probability x equals 0, plus 1 times the probability of 1 plus 2 times the probability of, I wouldn't write this much out if I were you, right? You probably skip to the other thing. I am just, again, being clear what this formula means, right? So that's, you do that, you will get 2.4. And that is the correct answer. But again, remember, this is a number more than 1, but that's okay, because is this a probability? No, right? This is the expected value. And these values of X, these corresponds to the numbers of chickens Juan has at his home. No, these correspond to the number of hours of television watched, right? So this is 2.4 what? Hours, right? Remember, that's your probability distribution, okay? Now, if I wanted to find the probability that somebody watches 2 or X is more, or well, okay. Less than or equal to 2, that's a different calculation. That would be one that's much easier. But students make this mistake, right? It is simply the probability that you watch exactly 2 hours plus the probability you watch exactly 3 plus which should equal 60.69. Okay. Common mistake students make, right? No one does this before I teach them the expected value formula, right? Is they would say probability, they would do this, but they would actually, instead of doing what I just did, they would end up doing what I did, but like, they would use this, they would do that, right? And now students typically understand if they get an answer more than 1 that it's wrong, but sometimes that's not. So, right, when you're finding the probability of an event, just add up the probability of the different parts of the distribution. When you are finding by the expected value, you multiply, right? Remember, when you multiply this by this, you are no longer getting a probability, right? Because you're multiplying a probability by something, by an amount of something. So it's no longer a probability, right? So please, another thing you can know is when I'm doing that multiplication and adding, I never truncate. If I'm truncating, I should just be adding. Does everyone get why we multiply here, but we don't here? Does everyone understand this distinction, right? Because this first thing is an amount of hours. The second thing is a probability, right? 69% of the time, a person will watch more than 2 hours. That doesn't, I shouldn't be multiplying in the 2, right? Like that doesn't make any sense. But students will do the purple calculation by adding the numbers that I've put together in the purple box, right? Which is incorrect. Does everyone understand why a student might make this mistake? Because it's similar, right? You're adding, but you do not for expected value. Questions here? Okay, so, right? So, remember, a parameter statistic, right, is a number that is acquired in the lab, right? So if I am trying to estimate the probability, no, sorry, not probability. If I'm trying to estimate the mean height of a human being by taking your mean height, that is the mean height of some of the populations, right? That is called a statistic. Whatever the mean height of every person on the planet, that would be a parameter. Does everyone understand the distinction, right? So we use statistics to estimate parameters, right? With a probability distribution, we have everybody, right? So it is a population, right? So the mean, standard deviation, and variance of a population distribution is a parameter, not a statistic, right? And you can conceptualize it, right? So supposing this isn't a survey, somehow this is like actually the percentages of people who watch this amount of TV, right? And I said, what is the mean amount of television hours watched, right? You would say, okay, 10% of people watch 0, so I should weight this with a 10%, right? This one with a 21%, et cetera, right? So notice this is a weighted mean, and it gives you the mean amount of hours a person watches television, right? Does everyone understand that? Right? That's a weighted mean. But this represents everybody, not just our sample. So the mean and variance of a discrete probability distribution can be found with these following formulas. Notice this formula right here for the mean is the same formula as for the, what is this the formula? What did I just tell you to find in the previous example? This is expected, sorry, I don't know why I said that. Expected value, right? Does everyone see this is the same thing? Mean and expected value for a probability distribution is the same thing, right? Because, right, I expect per play to get 67 cents. No, not really. That means I would average out 67 cents per play. So that is the mean of all my plays I would expect to have, right? Expected value and mean is the same thing, right? So in a distribution, you have mean, right? We also like to characterize how, so that tells you where your distribution is centered, right? There's also how much it's spread. There could be a different game that Drippy could say, which is, I'm going to play a game where every time you raise your hand, I'm going to give, Drippy is going to give you 67 cents, right? That would have the same mean as playing that game, but it would not be the same distribution, right? Because in one case, the exact same thing happens every time. In the other case, the mean is that, but different things happen different times. So the other thing, right, we have the center, we also have how spread out. So what do we use to measure how spread out a set of data is or a population is? We spent like an entire unit talking about this. How do we measure, what is the measure we use for spread? Standard deviation or variance, right? So probability distributions also have a standard deviation. So the other parameter is the variance. Right? So the variance, right, is the square of the standard. So it's easier to calculate the variance, right? This is what they say for, that's easier to format to understand, because here you're saying how different is a particular play than the mean. You're squaring it, and then you're weighting it according to the probability, right? but that's difficult to calculate. This one's much easier to calculate, right? So that's how you get your variance. So notice if there were not a 2 here, this would be your mean, right? So instead of, I'll show you an example. So instead of multiplying x, right, by the probability of x, you square that value and you multiply it by the probability of x, right? And you do that for each of them, then you subtract the mean squared, and then you get the standard deviation, right? You really only need to remember this formula, right? You don't need to, because you're going to be doing computing, right? So this is what you need to remember. And then if you just remember the standard deviation is the square root of the variance, notice this formula, the inside here is the same, right? So really there's only one formula you need to have memorized. So let's do an example where we calculate the mean, aka the expected value, and the variance of a probability distribution. And let's use another game type example. Questions here though. This is really the only formula you need. And again, these are all posted on Canvas, so you don't need to write down every single thing here. It's also in your online textbook, so don't overwrite, because I do need to move on. Okay, so let's suppose there's a fundraiser that is for the local symphony, right? The symphony is raffling off a couple of different things, right? The concert box seat, right? They're having seats, right, for to watch the symphony, right? These are nice seats. They cost $400, right? They're also raffling off a dinner, which is worth $100. Now, 2 CDs aren't worth anything now, but I don't know when the example that they did here. They're also raffling off 2 different CDs, each of which is somehow worth $20, right? And they sold $2,000 of tickets, right? So, and each ticket is $1. So let's find we want to find the expected value for someone who is buying a single raffle ticket, right? Now, first, would we expect the expected value? Do we think before even calculating it, should the expected value be negative or positive here? Well, so the game is in the perspective of you, the person buying a raffle ticket, right? The whole purpose of this situation is to do what? To the fundraiser. It's in the name. The whole purpose is to rank money if you are the symphony, right? If you are the player, then you should be well, you would like to win, right? But on average, you're going to be losing money. Otherwise, right, this thing isn't going to raise anything, right? If the prizes cost more than the raffle tickets, right? So we should expect, right? And you know this, right? It's kind of fun to gamble a little bit, but you know when it's a fundraiser, right, that you know that the expected value of a ticket is negative, right? So we should expect to have a negative answer here, right? Does everyone understand why we expect a negative answer? Because the purpose is to raise funds by the symphony, so you as player, right, would be expecting to lose money, right? So again, when you do these games, E is, right, this is just means change, right? Maybe you know that. Change in net worth, right? And that's in dollars, right? So to find the mean and the variance, we have different calculations, but the mean is the same thing as everybody, mean of a probability distribution is the same thing as everybody, expected value. Okay, So first we have to create the distribution. So we have X, and I'm just putting here, X is measured in dollars, right? And then the probability of acquiring that amount, right? So this probability distribution is going to be more complicated than before, right? So there are 3 different prizes worth different amounts of money, right? So there are how many different values of X? We think 3, but you could win any of the 3 prizes or win nothing, right? So there are actually 4 different possibilities, right? Everyone see that? All right, so let's start with the smallest value, right? So the smallest value, so you buy this ticket, and most likely what happens? Nothing, right? So buying a ticket and not winning a prize is an X value of, similar to the Drippy game, it is -1, right? Now, I've taught statistics before. I had students come up with their own game and calculate the expected value, right? But it's too many to grade for this class. Okay, so -1. Now let's go with if you win, right, from the smallest. So the smallest prize here is the CDs. That has a what value associated with it? Is it correct for me to write 20 here? Everybody's 20 correct. The correct value is not 40, because you're not winning 2 CDs. 2 separate people are winning each of the CDs. You understand what I'm saying here? And it's closer, it is 19, right? Because even if you win the CD, right, you spend $1 on that ticket, right? So you gained $19 in value. I guess that could be confusing, right? I interpreted it, and the textbook author that I got this problem from interpreted it as 2 tickets, each winning a CD. Why you'd want to have 2 of the same CD, I don't know, right? So that's how I'm interpreting it. But I could see it's not completely clear, right? And then the dinner, the value associated with that would be 9, and then the box seats would be, all right, so then we just need the probability for each of these. It'll be easier to do this actually kind of backwards. So the probability of winning the CD is what out of what? 2 out of 2,000, right? Which reduces to 1 out of 1,000. And then these other ones would be 1 out of 2,000, right? Because one person can win these out of the 2,000. One person will win this. Which means how many of the tickets don't win? All but 4, right? So the probability here would be out of 2,000. So that's the distribution. So let's start with the mean. So mean is the same thing as expected value. And that is equal to the sums of X times Okay. So let's do this. This would be that reduces to 1,000. So my pen's all of a sudden very slow. This ends up getting you which is equal to 73 cents, negative 73 cents. So I mean, you could buy more tickets. That's not quite it because each ticket that like loses, the next one's more likely to win. But if you could replay this day, right, where you go like Groundhog's Day, the movie, right, where you go play this raffle every day, but it really is different each time, right? You would average out losing 73 cents each time you played this raffle, right? Obviously, you never lose exactly 73 cents, right? But that is the expected value, right? So that is what you expect to happen every time you play this game. That is the center of your probability distribution, right? We cool on that and how we calculated that, right? Now, the other thing we need to calculate here is the mean, is the variance, right, and the standard deviation. Why is my pen so slow today? All right. Let's do this and then change. The pen is too slow. Because I'm having issue with computer, let's take our 5-minute break right now and I will finish this example and then we will come back to it, right? Okay, so let's get back at it. So we found the mean, and then remember the formula for the variance is similar, but not quite. It's a little different, right? So the one thing is we have that subtraction, right? The other thing is that we're doing the squares instead of the values themselves. So here, this would be -1 squared. I'm going to write out -1 squared. If you're calculating this out, I would expect you just to change that to like 1 in your head, right? So times the probability of that amount plus 19 squared, whatever that is, it's a little bit less than 400, times the probability of that amount. So that's this part, right? But then notice you also, so that's that part, right? And then you also do the part where you subtract the mean squared, which we found out before is 73 cents. So that's point. Wow, it is just still doing the thing. Okay, great. When you calculate this out, you get approximately 85. So that is your variance, right? So you take the square root of 85. That gives you approximately 9.23. Now, we measured, remember your variance is in the same unit. So our variance is in, sorry, not the standard deviation is measured in dollars. And notice your standard deviation and your variance will always be positive, right? Because they come from, we're squaring the negative values. Notice that this standard deviation is very large compared to the mean or the expected value, right? And that makes sense because if you look out at the possibilities, they're very spread out, right? This is considered something that's a very, like if you had a regular data set, this would be unusual, right? If I drew this out, it would be thousands of numbers, right? The vast majority of which would be -1. Every so often I have a 19 pop up, and then even more rarely I have a 99 or a 399 pop up, right? I should have a very big variance because my numbers range from -1 to 399, right? And remember, we said that the variance isn't outlier resistant, nor should it be, right? So these outliers pull that variance away from 0, which would be if we just had this part, to something much larger, right? $9. So we are saying, okay, the change in net worth has a mean of 0.073, right? -0.073. So the mean situation is you lose a little less than $1, right? And the standard deviation of those plays is like $9. So that's a lot. Okay, we're not going to get too far. Great. Okay. Questions here? All right. So try to go through this next part quickly so we can at least start the binomial story. All right. Fair game. A fair game is a game that has an expected value of 0, roughly, right? So neither of the games I show had an expected value of 0, right? No fundraiser is going to be a fair game, right? No casino offers a fair game, right? Because otherwise the casino wouldn't make any money, right? Each casino game has expected winnings for the house, right? So the average, that's 1.5 cents per play, right, to 60 cents. Right? So that's what a fair game would be, right? So a fair game would be one that you'd be indifferent, if you don't care about the risk, right, that you'd be indifferent between playing or not playing, right? So if I offer Michelle a fair game, I flip a coin, right? If it's heads, I give you $100. If it's tails, you give me $100. That's a fair game. And the expected value for that game would be $0, right? But the variance would be bigger the more we decide to wager on it, right? So the variance is kind of a measure of the variance, or standard deviation is more of a measure of the risk in the game if you're thinking about a game. Questions? I think fair game's pretty straightforward. So let's just talk about. So imagine you're doing something like, imagine your probability distribution, for example, here is flipping 100 coins, right? If the probability, right, of a particular value, right, same thing here, right? You can take the standard deviation, add or subtract 2 from it, right? If it is more than 2 standard deviations away from the mean of your probability distribution, that's exceptionally high. 2 lower, exceptionally low. Same thing as before, right? So we did this before, right? No, that's for, yeah. So what's significantly high and significantly low in these situations? It's different. So let's say that you have a probability distribution of flipping 100 coins, right? And you said, okay, I got 60 heads. Is that a significant amount of heads, right? So you calculate what's the probability that you get exactly 60 heads, 61, 62, 63, 64. Add those all up to 100. If those probabilities add up to less than 5%, right, that's significantly high, right? So if getting X or more is less than 5%, that's significantly high. Likewise, if getting X or fewer is less than 5%, that's significantly low, right? This value isn't rigid. What do you use this for? Well, this is the inferential statistics, right? So we'll do this later, right? With these probability distributions, we don't really know, right? Unless you have like a game that's this simple, we don't really know what the probability distribution is. You are kind of making a hypothesis, right? And then you can do that by actually testing it. So let's say, given a particular assumption, right, that some distribution is, if the probability that a particular outcome that actually has occurred is significantly small, we assume that our assumption was incorrect in the first place. That's what the rule for inferential statistics. That's very confusing without giving you a specific example, right? So let's assume I'm flipping a coin 30 times, right? And the assumption would be that the coin is fair, right? 50% of the times it's a heads, 50% of the times it's a tail, right? We could create it. We did this for 2 flips, right? It would take a lot of work, but you could create a actually, we'll learn how to do that later today, actually. You could create a probability distribution for where we assign a probability for each amount of heads, right? You have a table, probability of 0 heads, 1 head, 2 head, 3. You understand what I'm saying, right? Let's say we actually flip it and it comes up 26 times. Well, we can then calculate it, right? If we did that distribution, right, we find the probability of getting exactly 26 heads, so it happened 26 times, right? We want to find out what's the probability that this event that actually occurred would occur by chance, right? And we classify that event as 26 or more times. So you take the probability of 26, add the probability of 27, 28, 29, 30. You add all those probabilities together, you get a probability of 0.00003. That is a very small probability. So is this probability, so this would be considered significantly more heads than we expect, right? And it's a lot more. So we conclude that the coin is not fair, right? We'll be doing this later. This probability, if this coin were fair, the probability of this happening is so low that we assume that our previous assumption that the coin is fair is incorrect. If we somehow knew coin was fair, we would know, hey, this is just an unlikely event that happened, right? But in this case, right, so this is inferential statistics. If something happens, an event actually occurs that has a probability of less than 5% occurring that much or that little, we assume that our previous assumption was wrong. Now, that 5%, you might say that's not conservative. Events with probability of 5% happen not that uncommonly. you might be right. Then if you want to be more careful about rejecting your hypothesis, make it 0.1 or 0.01. Does everyone understand what I'm saying here? Okay, so let's move on to our next. So that is 5.1. Let's move on to 5.2. So we've talked about probability distributions, right? And I've just given you the distribution. We figured it out by hand, right? The example I said with the flipping the coin, that's actually an example of a binomial probability distribution. So a binomial probability distribution is by far the most common discrete probability distribution, right? And we will tell, so we will kind of give a couple of things here. We will define what a binomial experiment is. We will calculate a binomial probability. We will calculate the expected value of a binomial experiment and the standard deviation of a binomial experiment, right? Binomial has the prefix bi, which means 2, right? So first off, it is something that has 2 possible outcomes, right? So let me give you an example of something that is a binomial distribution, or it should be pretty similar to one. Let's talk about free throw shooting, right? So your cousin Drippy is probably just about as good at basketball as I am, right? Which is not very good. Free throw shots, right? Those of you who play basketball will know that you're supposed to make the vast majority of your foul shots, right? Free throws from the foul line. So when Drippy plays basketball, right, the probability he will sink a free throw, right, is 0.57, right, or 57%, okay? So a question could be, let's assume he's doing 5 different free throws, right? What's the probability he makes 4 out of 5 of these? Exactly 4 out of 5. Well, this is a probability distribution because what are the possibilities? The possibilities are he either makes no free throws, 1 free throw, 2 free throws, 3, 4, or 5, right? So clearly this is a probability distribution where X is the number of free throws made. Right? And so the question is, how do I assign the numbers to that? That's what we're going to figure out, right? This is the assumption of a binomial experiment, right? And this is why this is considered a binomial experiment. There are 4 things, right? 1, in a binomial, you are doing, or something is happening, you're doing the same thing over and over again, right? So in this case, he's shooting a free throw from the foul line, right? If it was something where like, hey, if he makes it, he has to back up further, right? Or horse, where you're making different types of shots, that's not a binomial experiment. A binomial experiment also only has 2 outcomes. Here they say success and failure, but it's obviously arbitrary, right? Flipping a coin, there are 2 outcomes, heads or tails, right? It doesn't matter that one's considered a success, right? Here it's clear what's a success, what's not. I'm flipping a coin. Notice there's still 2 possible outcomes. So really, you don't need to focus on the success or failure part. The probability of a success is constant, right? So in this case, that's not clear, right? If Drippy shoots a free throw and he misses to the left, maybe he adjusts so he doesn't do the same thing again, right? So we're making some assumption that Drippy, once he has veins of is ice in his blood, right? He does not get nervous if he keeps missing, right? He also is not very bright, so he doesn't know how to adjust, right? So you get this, right? This is the assumption, is that each trial is independent, right? So whether I make the first free throw does not affect the probability I make the second or the fourth, right? So the repeated trials are independent, which means the probability of each trial has to be the same, right? So a lot of times things can be modeled by a binomial experiment, right? So flipping a coin is a binomial experiment, right? Actually the game where we have the like values, right? If I roll a die, right, a certain number of times, right? That can also be binomial if I say like I'm either getting a 1 or a not a 1, right? Because then, sure, I could get 6 different things, but really I'm assigning 5 of those 6 to be a failure, right? Does everyone understand like a binomial? Notice a lot of things are like this, right? So this is an example of one where there are a fixed number of times. In this case, it's 5, right? And in this case, there is a fixed, the probability of a success for each trial is constant. In this case, 0.57. And for it to be constant, then each trial has to be independent, right? All right, so let's try to break this down, right? So we know it's a binomial probability distribution. We just don't know what the probabilities of each of these things are, right? So let's try to figure out, I'm going to give you some guided question that will help you figure out how to calculate this, right? So we are trying to figure out what's the probability, right? He makes exactly 4 of 5 free throws, right? So basically, if X is the number of free throws being made, I'm trying to figure out what's the probability that X is equal to 4. Oh my God, there's a giant goose just flew right up here. Sorry. Okay, now it's, don't get to see it. It's just all to ask. All right, there we go. All right. Now this is the first time this has happened to me. Okay. So to find out the probability, we might want to figure out how many ways something can happen. So how many different ways could he make exactly 4 of 5 free throws? I'll give you a hint. Here's one way. He could miss the first shot and then make the next 4. Or he could make the first shot, miss, and then miss the next 3. So how many different ways are there for him to make exactly 4 out of 5? 5, right? Because it's just, where is that miss going to be? Now, are any of these more like, so we just said that it's independent, right? He doesn't learn, he doesn't have nerves, right? Are any one of these 5 possibilities more likely than the other one? No. So if I can find out the probability of one of these, I can just multiply it by 5 to get the probability he'd get exactly 4 out of 5. So let's focus on this last one. Or let's see. Well, let's do the first one. Yep. Okay, so what's the probability of missing his first free throw and then making the next 4? Well, we said these are independent events, right? So when you have independent events happening sequentially, you can just do what with the probabilities? Add them, subtract them, multiply them. We having an event, right? So you flip a coin, you get 2 heads 1/4 of the time because it's 1/2 times 1/2, right? So we can just multiply does everyone see you can just multiply here? So let's do that. So what's the probability that he will miss his first free throw as a decimal? Everybody? 0. 4-3, right? He makes 57% of his free throws, so he misses 43. So the probability he will miss his first shot is 43, right? Or 0.43. Now, what's the probability then he makes the next 4? So if he misses the first shot 43% of the time, right, he will make his next shot 57%. So if we're just looking at the probability that he would, right? So what's the probability? A miss and then a make, right? Well, 43% of the time, the first shot would be a miss. And then of that 43%, 57% would be. So when you're having successive independent events, you just multiply. So that's the probability of the second. And then the probability he makes his third shot is 0.57 times again. Then again, 0.57, okay. Notice an easier way for me to write this would have been to write 0.43 times 0.57 to the power of 4. If you do that, you get about a number that's roughly around 4.5%. So is that the answer to the probability that he will make exactly 4 out of 5 shots? It is not. This is the probability that he will miss his first free throw and make the next 4, right? But is that the only way to make 4 out of 5 free throws? How many ways are there? 5, and they're each equally likely, right? So the answer so about 23%. Okay. So we can kind of see some patterns here, right? Any questions about why anything is the way that it is? And anybody? So look at this. This is the probability of a miss, then 4 makes, right? Then 4 successes. And I'm multiplying by 5 because there are 5 different ways that event, right? There are 5 different ways. So this ends up equaling the probability that x is equal to 4, where 4 is the number of free throws he makes. Okay, questions? It's tricky, all right? You don't have to go through the reasoning. This is going to come to a formula, but again, if I just give it to you, it's just magic, right? So let's try to reason through it.